All right, friends, how are you? I hope you're all doing wonderful. So, welcome back to this particular channel of Pradhan Academy. So, we are live again with a new video and a new content. Today, we're going to be discussing about relations and functions, right? So, I hope I'm audible to all of you. All right, friends, how are you? Fine. So, yeah, I am able to see your live chats. So, so let me know if you're ready. We can start. So, as of the last lecture, so we have already covered in the last session, we have covered the continuity and differentiability part, right? So we saw that how easy and simple are the questions from the chapters of continuity and differentiability, right? So and also along with that, we also tried to analyze what was the paper pattern, right? So today we are basically at the end part of covering the relation and functions. So apart from this relation functions, we have covered almost all the chapters, right? So if you look at your CBSE syllabus, we have started with the probability, applications of integrals, differential equations, probability. We have already covered vectors and 3D geometry. We have covered applications of derivative. We have covered continuity and differentiability, right? So we are left with to cover only one part, that is relations and functions, right? So let's start with relations and functions in today's session. So I'm the instructor for this course and I will be discussing about relations and functions, right? So please, if you are someone who is new to this particular channel and if you are starting watching the session from this particular video, do consider subscribing to the particular channel and don't forget to hit the bell icon, okay? So that you don't miss out any upcoming notifications. Fine. Please let me know if you are clear to go with it. All right. Shall we proceed then? Okay, so let us proceed with the session on relation and function. So before we start with relation and function, I'll be having a small kind of recap on what is the different type of relations and what are basically called relations. Then we move on to the how to classify different types of relations, which is very important for your board examinations. And even if you look at the functions chapter, the part of the functions where to classify the type of the functions as one function or many one function, or you have to classify as onto function or an into function, or whether it is a surjective map or an injective map, right? And or whether it is a bijective kind of map or not, or with the bijective map can I get the inverse of a function. That is all what we are going to discuss in this today's sessions, okay? So if you haven't started studying the chapter of functions and relations, you can watch this particular lecture to the till the end, okay? Please try to focus on this particular questions what I'm basically discussing. These are the top important previous year problems, okay? And I will be solving the previous year problem with you, and I will make you understand that how simple are these problems for your exams, okay? So with this you can start for your preparation. So let's get started on this particular content. So with this, today our goal is basically to analyze the relation function chapter. We are also going to understand the sets and the relation, because you know ultimately these are all basic sets, and set terminologies are basically important in order to start with the relations part, right? After that, we are also going to discuss about the idea of functions, right? So how are we basically getting a function from a particular relation? That is what we're going to discuss. And after that, we're going to be discussing about the different types of functions, and also we're going to also see about how we can get the inverse of function given that a function is a bijective function. Okay, so also we're going to focus on some of the techniques on solving different types of problems. So I will be showing you some of the most frequently asked problems. So if you just look at those problems and prepare those problems nicely, you are basically ready to go with the contents, okay? Also apart from that, I will be discussing about the exam pattern and the paper analysis that you are going to have it after the class is over, okay? So let's start with this particular content. Okay, so if you are ready to start, please give me a thumbs up in the live chat. Okay, so let's start with this. All right, so let us go proceeding with the topic of relation functions, right? So before we start about the discussing about the topic of relation function, I would quickly recap on what is relation, right? So if you recall from your earlier class 11th, right? So in a sets, if you have two sets, let us call you have one set as A and another set as B, right? Now in a sets, you know that there is an operator called as Cartesian product. Why, which is basically, so if you do Cartesian product of two sets, it is basically a set of all the ordered pairs of elements where A is coming from set A and B is coming from set B, right? So I will write it A is basically belonging to set A and B is basically belonging to set B. So whenever I do A cross B, it is basically ordered pair A comma B, right? Similarly, when I do Cartesian product B cross A, it is basically B comma A, right? Where B is coming from the set B and small a is coming from set A, right? So this is something that we have already studied as the set of Cartesian product, right? This is something called as Cartesian product. So if you recall your definitions of relations, so relations are nothing but they are subsets or sets or all of the subsets of a particular Cartesian product. Okay, so relations are basically subsets of Cartesian product. Okay, so that's how the simply definition of relation is basically given as relations are basically subsets. Okay, subsets of what? Cartesian product. So whenever I say or I try to define, let us say I am defining a relation from set A to set B. Okay, and whenever I need to define a relation, I should write the name of the relation as R such that it goes from set A to set B. So I denote it like this. Okay, this basically implies that a relation from set A to B. Okay, so whenever I basically try to imply R of A goes to B, it basically means the relation goes from set A to set B. Okay, so if this is clear, right? So now what is basic? Then all the Cartesian product, we perform the Cartesian product of A cross B, and then all the possible subsets of A cross B are basically called as relations from A to B, right? Now in a particular relations, we have that on the basis of the type of map or on the basis of the type of map, relations are generally classified into three different types. First of them is basically called as a reflexive relation. So what is a reflexive relation? A reflexive relation is a relation which is defined on set A is said to be reflexive. It's said to be reflexive if x comma x belongs to that particular relation. So for example, if I have a relation on A cross B and I say that x comma y basically belongs to that particular relation. Okay, so x comma y belongs to the particular relation, then for every, so it is basically said to be reflexive on set A when every element of A, so x is an element of A, so every element of A has its x comma x will basically lie or will belong to the relation. So for all x belonging to the particular set A, all the x are related to itself. That is called as reflexive relation. So whenever all the elements of set A or the domain set is basically related to itself in the codomain set, then that particular relation is known as reflexive relation, right? Similarly, we also have something called as symmetric relation. Now symmetric relation is said to symmetric relation is basically a type of relation on set A is said to be symmetric if, for example, now if I say that x comma y basically belongs to the particular set relation R, then it will also imply that if it is a reflexive, it's a symmetric relation, then y comma x will also belongs to R, where x and y both belongs to set A, where x and y both belongs to set A. Okay, so what does it basically means? It basically means that if you just take the reverse of the elements of the domain and the codomain, those elements will also belong to the particular set or the relation. Okay, so that kind of relation where x is related to y and y is also related to x, those kind of relation for all x and y belong to the relation, those kind of relations we call or generally classify it as symmetric relation. I hope this is clear. Okay, now once we understand this part, let's now try to understand what is transitive relation. Now transitive relation is another type of relation which is defined on the set A is said to be transitive if x comma y belongs to the particular relation and also y comma z also belong to the particular relation, then is x comma z will also belong to the relation for all x y z belongs to the set A. That is, if x is related to y, y is related to z, then x should be related to z for a transitive relation. So for a particular transitive relation, x and y related, y and z related, so x and z should be related. That's it. Okay, so with the idea of this particular three types of relations, then we have the equivalence relation defined as a relation which on set A is said to be equivalence when it is satisfying all the three types of relations. That is, it is reflexive, it is symmetric, and as well as it is transitive. So if it is satisfied all these three types of relations, then it is basically called as equivalence relation. Okay, so we basically define equivalent relation as a relation which satisfy reflexive, symmetric and transitive criteria. I hope this part is clear. Okay, please let me know in the comment section if this is not clear. I hope this part is clear, right? Is this clear? Let me know in the comments, in the live chats. If you have any query or issue, please tell me. Okay, so once you understand this part of the relation, then now we can proceed for the next part, which is basically a particular relation is therefore classified into functions, right? So functions are basically nothing but they are special relations such that, so in this particular relation, we basically, from this particular relation, from this relation, we basically try to classify functions as, functions as, so we basically get functions from relations as, these are basically special relations given that for all equivalent input in the given domain, we basically have a corresponding output in the codomain, right? So basically functions are known as special relations for which for all inputs given into the domain, we will definitely have a output in the codomain, right? So that is basically our function. So basically function is said that for every input, we definitely have an output, right? So that those are basically defined as functions. So that is it. Then once we understand functions, let's now try to understand the different types of functions, right? So we basically now classify the functions based on the type of map into various types. That is, one is called as one-one function or injective function, and the second one is the onto function or the surjective function, right? Now let us try to understand what is a one-one function or injective function. A particular function which is going from set x to set y, that is x is the domain. Whenever we define any particular notation like this, x is basically a domain and y is basically the codomain. Okay, so let me write it over here. So whenever I represent a function, I will define the function like this, given the name of the function f, and it is going from particular domain to the codomain, right? So the set which I am writing from where it is going, it is basically called as domain set, right? And the set from where it is basically mapped to, it is basically called as codomain, right? Now for a particular function to be one-one function, to be a one-one function, it understands that if the images of the distinct elements of x under f are basically distinct, that is f of x1 is equal to f of x2, such that x1 is equal to x2. Now I will have the value of the function output at x1 and x2 as same if and only if the given input x1 and x2 are same, right? So that is basically mean that all the images that I'm giving for a distinct element in x will be distinct, right? So that is basically called as one-one function. Now a function which is not a one-one function is basically known as a many-one function, right? Now this is basically about the type of map on the dependence on the type of the input given in the domain, right? Now once we understand this, let's now try to focus what is the onto function. Onto function, also known as surjective function. The onto function is basically, so for a function going from set x to set y is said to be an onto function or a surjective function if for every element of y is basically image of some element of set x under f. Okay, now if you just try to understand this, what does this basically means is that a particular function for which if I'm having all the range is basically equal to the codomain, then that particular function is known as a onto function. So when I have range is equal to codomain, then that kind of function is basically called as a surjective map or basically a onto function. That is, for every element of y is an image of some element of x under f. That is, for every y belonging to this set capital Y, there exists a element x in the small x such that f of x is basically equal to y. Okay, and the function basically it is saying the same thing. Onto function is basically when the range is equal to its codomain, right? And the function which is not an onto function is basically called as into function, right? Now once we understand this, we need to try to understand what is a bijective function or a one-one and onto function. So a bijective function is a function which is both one-one as well as onto. So a function which is both one-one and onto, this kind of function are basically known as bijective map. And for bijective map, I will only have the inverse possible. So inverse of of function is possible only for bijective map. Okay. Now, a bijective map will only have its inverse possible, right? Now, now let us try to understand what is a composition of function or what is composite function, right? And this is also important, keeping in set the board examination patterns, right? So, if I have one function which is going from set A to set Y, and there is another function G, so one function is F and another function is G, which is going from set Y to Z. So what do you understand is that the image of this X is basically Y, and this Y is basically given as a domain or input of the G, and then output is given as Z. So let us say these are the two functions, then the composition of F and G is a function from capital set X to set Y, Z, which is denoted by F of G, which is also known as F of G of X, right? So what you see over here is basically whatever output I'm getting for Y is basically given as an input for G, right? But what we understand over here is basically called as the composition of function, right? So the output of G, um, yeah, that this is something wrong over here. Okay, please correct it. Actually, it should be like the output of so if you are writing f of g, that is basically f of g of x, then basically the output of g of x is basically the input for f of x, right? But in this particular definition over here, if you see over the defined way, that is x having the output as y and y is the given input for g, then this kind of relation is only for the composite function g of f of x, because the output for f is basically y, which is an input for g, right? So that is something that you need to understand for defining a composite relation, right? Now, it is very important to understand that in general, the composite of f of g of x is not equal to g of f of x, right? Also, one more thing to be noted over here is that in general, g of x is basically 1, 1 implies that f is 1, 1 and g of f is onto, simply that g is onto, right? So, for getting 1, 1, the input should be 1, 1. So, in a composite function, for getting a 1, 1 function of a composite function, the input should be 1, 1. And for getting a onto on the composite function, the output should be 1, 1. That means the final function should be an onto function, right? Right. So this is something that is very crucial and input. Now, this is also something that you can form multiple composites of multiple functions, right? So this is all what we need to discuss or take a recap on the initial part of the functions. Now let us start with the previous year problems, right? So as you can see over here, we have the first problem on our screen. So if you look at the problem, it is said that I have a given function. I have a given function. Please refrain yourself from using these shortcuts or abbreviations like fxn. Please try to write the entire thing function while you're writing your actual paper. Okay. So it is said that given function is defined as f, which is going from positive real part to the real part, right? So positive real part to the real part, and it is basically defined as, okay, the defined function f of x defined as is basically defined as 4x plus 3, right? So it is basically defined as 4x plus 3. Now I have to comment on whether this particular function is a 1 1 function or an onto function or not of them, or which one of them, right? So initially, while we are starting with this understanding of how to solve the questions of 1 1 function, what is important to understand, now this is something that is for your understanding. Now please, you don't need to show all these calculations, right? So you can see this is basically linear function, and linear function are always 1 1 function, and it is always onto functions. Okay, it is not always onto function because the input to the function of the domain is basically positive real numbers. So therefore the output will also be a positive real number starting from 3, right? So therefore I won't have the all the real part, right? That is for the solution part. This is basically 1 1 1 1, but it is not an onto map. Okay, so it is basically 1 1 function but not onto. Okay, so therefore if you look at the options basically said that it is option number A which is correct. Okay, so the answer over here is basically option A. Okay, so it is basically 1 1 but not an onto. Now how did I quickly approach the answer? Now this is not how you are going to solve it, right? So whenever you have these kinds of questions, please try to, since it's a linear map, so you can definitely try to draw the graph of the function, right? So if you start drawing the graph of the function, now it is saying that it is starting from the non-negative real part, right? Non-negative real part is basically starting from 0 and going to the infinity, positive infinity, right? So at 0, if you look at this graph, the value is going to be equal to 3, and it is a linear function, and this is basically how it's going to increase, right, up to infinity. Now if you just look at this particular function, so first of all you will write over here the domain is x belongs to the positive real part, and the range is basically y belongs to 3 comma infinity, right? 3 is included and going to infinity. Now if you look at the range and the codomain, it is basically not equal to the codomain, right? So when a particular function's range is not equal to codomain, then we call that function is not an onto function, right? It's not an onto map, right? Now this was simple case, right, where you can easily find the range and the domain. The domain is already given and range was very simple, right? Now what if the question is pretty tricky and you are not getting the function and how you are basically going to approach the questions, right? So generally what we basically have seen that for 1 map, what you can see that a increasing or a decreasing function, if you look at increasing function or if you look at a decreasing function, these are generally 1 map. So how are you going to classify a 1 function is that whenever you draw a horizontal line, the point of intersection will be only one, right? So this is basically, you can say this point, these kinds of results will only be possible if you just try to draw f dash of x and it is greater than 0, or it is strictly increasing or strictly decreasing, like this case which is strictly decreasing, then only we will have only one point of intersection. Unlike the case when a function is like increasing and then remaining constant and then again increasing, here for this kind of set I will have multiple inputs, we will have the same output. So that is not the case for 1 1. This is 1 1, this is 1 1, this is not 1 1, right? So therefore, the check for seeing whether a particular function is 1 1 or not, we have in simple test is basically to perform the derivative and try to see whether it is always positive or always negative, right? So if you are getting either strictly increasing case or strictly decreasing case, then you can be sure that it is either a 1 1 function, right? Now our question is basically to understand about the onto function, right? So whenever we calculate for onto function, it is always recommended to all of you to basically try to calculate the range, right? So what you will do over here, you will try to calculate the range, okay? And once you find out the range, so how do you find out range? Range, for finding out range, the simple technique that is basically you can do is that for a given function y is equal to f of x, you basically try to represent x in terms of some function of y, okay? Now that necessarily need not be a inverse function. That is something that you need to understand, because for inverse that particular function need to be a bijective map, right? But what I'm going to do, I'm trying to represent this x in terms of y, so that will be some different function of y, which is I called it as g of y, right? Now I just need to get out that for a given input of x, what is the given, so for given input of x, what is the output y, right? So that can also be written as like in the next statement, what you can see that given input of y, what is the output of x, okay? So we know the output of x, this output is known to us because we know the input of x, right? So this input is known to us, the x is known to us, right? So I will write the x is known to us, so we have to only predict what is the given y. So x is known to us, this is basically known, right? This is the domain, right, which is known to us. Now given domain is known to us, what should be the given y? So that particular thing is unknown, and this is basically will give you the output of range, right? Now there is no fixed defined method or methodology to solve the problems of range, but what you want to understand is basically on different set of problems you have to apply different results, right? So if you are getting an increasing function, a strictly increasing function, then that particular function will be having the range going from the initial point to the ending point, right? Now that is something easy. But if you are not having if you are having combinations of increasing function, decreasing function, then in that case the range is basically the global maximum to the global minimum, right? So for calculating global maximum, global minimum, you definitely know the methods to solve for global maximum, global minimum, right? But that is only when the domain is bounded. So in unbounded domain, you are not able to do the same, right? What do you mean by unbounded domain? Unbounded domain is basically like this case, like in R positive or R or real number, right? Where the domain is unbounded, that is the maximum number that is possible is infinity, right? But infinity is not a number, it's basically an unbounded domain, right? So therefore you understand this particular problem. Now let us try to understand the next problem, right? So if you look at this problem over here, now here we have to basically solve for the given relation, which is basically a relation on set A, okay? Now let us try to define the problem. First of all, what you will do, now this is a given, it's a prove that type of question, and this was a plus 2 marker problem. Okay, so what you will do, you will write first of all the given statement. So given set A is basically consisting of elements 1, 2, 3, 4 and 5, right? So you have this given set A on this particular element, and the relation R is defined as x comma y such that x square minus y square mod of it is less than 8, right? So I have this given relation for x comma y such that x square minus y square mod of that, or the magnitude of x square minus y square, is less than 8, right? Now I have to classify whether this particular type of relation is a reflexive, symmetric and transitive, right? So how we are going to solve for the actual part of the exam? First of all, you will write it over here, reflexive. Okay, so we are checking for first of all reflexive, right? So if x, basically for x belonging to the set A, is x comma x also belonging to set relation A? So let us try to check for it. So that is basically, if I put x square and in place of y, if I put x, is this belonging to the relation? So that is x square minus y square mod of it, which is equal to a 0, and this is basically less than 8, right? Which is true. So therefore x comma x belongs to the relation. So therefore it is a reflexive map, right? Now we have to talk about a symmetric, right? Now we have to talk about a symmetric relation, right? So is it a symmetric or not? Let us try to understand. So if you look at x comma y belonging to the relation R, then is a y comma x also belong to the relation R? Let us check. So if I put in place of x, if I put y, and in place of x, if I put x, in place of y, if I put x, is this satisfying the relation? Yes, indeed it's satisfying the relation, because we have magnitude of it, right? So it doesn't matter whether we are subtracting x square from y square or y square from x square, because ultimately our goal is basically to obtain the magnitude. So therefore, yes, it is satisfying it, right? So we will try it over here, which is true, right? So therefore, this y comma x is also belong to the relation, right? So that's how you are going to classify this kind of relation as a symmetric relation, right? Now, once we understand the reflexive, symmetric, so this is also symmetric case, right? Now we will discuss about the transitive relation, right? Now for transitive, so if you recall the definition, that if I have x comma y belonging to the relation and y comma z also belong to the relation, then x comma z should also belong to the relation. Is it true for it? Let us check. So if I take element 1 and 2 and 3, so if I just try to find out 1 square minus 2 square, so 1 square minus 2 square is basically equal to 3, right? Minus of 3, so mod of it is 3, right? So that is basically satisfying this criteria. Similarly, if I take 2 square and 3 square, that is basically 9 minus 4, that is 5, is also satisfying the criteria, right? So is 1 and 3 satisfying the criteria? If you look at 1 and 3, so 3 square minus 1 is basically equal to 8. But 8 is less than 8? No, it is equal to 8, right? So therefore, if you look at the transitive type of relation, it is not satisfying the criteria for transitive relation, right? So it is not an equivalence relation. So you can say that it is a reflexive relation, it is a symmetric relation, but it is not a transitive relation, right? So that is how we are going to solve this problem in the actual examination. Now, please, when you are solving the problem, please make sure that you write all the given inputs in the given manner and you solve the steps step by step, right? If you have any questions, you can keep me posted in the live chat. Yeah, I'm going through your chats. Please let me know if you have any questions. So this part is clear, right? Okay, so fine. So if you have any no questions, let's proceed. Yeah, correct. So this is basically reflexive, symmetric, but not transitive, right? So we understand this particular type of relation now. Now let us see what are the different types of problems also you can get to see, right? So if you look at the paper, you are mostly going to see whether you have to classify a function as 1, 1, on 2, or whether you have to classify a relation into as symmetric relation and transitive, right? So those are the different set of problems that you are definitely going to encounter in the examinations, right? So let's try to now understand the problem given over here, right? So this is another problem which is a 3 marker problem, okay? So it is said that I have a function which is defined from which is defined from real part to the real part, such that the function is given as ax plus of b, okay? Ax plus of b. Now I have, in order to find out these two unknown A and B, I have been provided with the two given initial conditions or conditions over here, right? So it is said that f of 1 is equal to 1 and f of 2 is basically equal to 3, right? So if you just put these values, we'll get basically a plus b is equal to 1, and similarly I will get 2a plus b is equal to 3, right? So I can simply solve it and I can get this basically equal to a is equal to 2 and b is equal to minus of 1, right? So I get the given function as, so therefore, from here, I'll get the required function as 2x minus of 1, which is a linear map. Now, already I have told you many times that whenever I have a polynomial function, the particular polynomial function for a given domain, real number, it will always have the codomain or the range as a real number. So therefore, it is always a 1-1 function and always a, sorry, it's always a onto function, right? Now we have to basically check whether it is an so odd order polynomials. Okay, all odd order polynomials will always have the range is equal to the codomain for the given input of domain as real part, right? Because you know that if you look at the in general, if any order polynomial function is given, it is basically something like this, okay? But for even order polynomial, I will have some function like this, okay? So you can see for even order polynomial, the values, the range is always a positive number, right? So depending on the given, so it is an even order polynomial and this is an odd order, okay? So for order, the entire range is basically minus infinity to plus infinity. But for even order, the range is 0 to infinity, right? So that is something that you need to understand. But if you look at this particular function over here, we have the given function, which is a linear function, right? So for a linear function, it is always an 1-1 function. And since given that domain is real part R and the codomain is also R, so if you put all the R, you can see. So first of all, let me write it over here. The domain is all R, right? So similarly, if the domain is all R, I will have the range is also, the range of y will also be all real number, that is minus infinity to plus infinity, right? So here what we can see that the range is basically equal to codomain, right? So whenever I have the range is basically equal to codomain, then that kind of function is basically as onto function, right? So therefore this is basically both 1-1 and onto function, right? Now why it is 1-1? Because it's a linear function. So if you get test a vertical, the horizontal line test, you will see that the horizontal line always intersected only at one particular point, right? Also you can just go by the derivative test, that is if you differentiate the function, you're getting a positive result, which is basically a strictly increasing function, right? So that's how we're going to say that it is a 1-1 function as well. I hope this part of the solution is clear, right? So if this is clear, please let me know in the live chats. So I'm basically going through your live chat. I hope this part of the solution is clear, right? This is fairly simple. Okay. This is very much simple and you just need to apply your fundamental concepts. Okay. So what you can see that this is the type of the question that are basically repeated mostly. Okay. So if you are just preparing, if you haven't prepared anything, and if you think of preparing or starting a preparation just now, what I would say is that please try to focus more on the classification of functions or as a type of map. Also, please focus on the inverse function and composite function. And for relation, please try to focus more on the type of relations. Okay. Let us now proceed with the next problem. So next problem is not much related to functions, but I took this problem to explain you that there is a concept of functions also in the questions of derivative, right? So if you just look at this particular problem, this is a problem from the previous year 2024 paper. Here in this problem, it's a 4-marker problem. So we have to basically prove that dy by dx, am I getting this particular relation or not, right? So first of all, you will write the given relation, okay? First of all, the given relation is given as square root of 1 minus x square plus square root of 1 minus y square is basically equal to a times of x minus y, right? So if I have this given relation, then I have to prove, okay, to prove that I'm getting the derivative of y with respect to x as square root of 1 minus y square divided by 1 minus x square, right? So in order to prove this result, what you're basically going to do it over here is that let us write it as proof. So while we start the proof, we basically need to understand that what is the way to solve this problem, right? Now, if you have a square root function, if the first and foremost analysis you should do is basically to try to find out what is the domain. What is the domain for the square root function, right? So if you look at a domain, so the inside part or what is the input of this domain, the square root should be positive part, right? So therefore, if you look at over here, so here 1 minus x squared should be a greater than or equal to 0. Similarly, 1 minus y square also should be greater than or equal to 0 for domain. Okay, this is for domain, right? Because we are dealing with real numbers, so therefore for domain 1 minus x square should be greater than equal to 0 and 1 minus y square should also be greater than equal to 0, right? So from here, which narrows down my cases of x basically between -1 to 1, and similarly the y is also between -1 to 1, right? Now in order to prove this particular relation, what I'm going to do is basically I will try to differentiate this relation, this entire relation with respect to y. So if I just try to differentiate with respect to x, sorry, so we know the square root of differentiation of square root of x is basically 1 upon 2 square root of x, right? Which is basically going to be like this. And then by using chain rule, I will write it over here minus of 2x, right? Then plus of 1 upon 2 times of square root of 1 minus y square into minus 2y dy by dx, right? Because I'm differentiating with respect to x, which is equals to a times of, so it is x minus y, so it is basically 1 minus, so 1 minus dy upon dx, right? Now we have to basically find out this dy upon dx, right? So what we'll do, we will try to club the dy by dx term and the other term to the one side. So if you just try to see the expression over here, it is basically y upon square root of 1 minus y square 1 minus y square dy by dx, right? So what I'm doing, I'm taking this part on the right hand side and this a part on the left hand side. So if you just do the same, or you can do the other part as well, so you can take this part on the left hand side. So this is basically going to become a times of, so it is going to basically simply become a minus y by square root of 1 minus y square dy by dx is equals to a plus x upon square root of 1 minus x square, right? So it is basically like this, right? Now we have to basically calculate or find out this dy upon dx, right? Now how are we going to again do from here is basically a problem part, right? Now from here what we see, that we need to prove the given expression as dy upon dx as 1 minus y square by 1 minus x square in the square root term, right? So what I'm going to do over here is a very simple, so please let me know if this is clear or not. I'm just going through your live chats. Is this part of the solution clear to you, right? Is it clear? Okay. So now, so once we understand this part, now our next goal is to understand what are we getting, for different sets of x and y, right? Now if you recall your initial classes of integrals, I have discussed about something, a very important thing, that is called as substitution, right? So I told you that whenever I will have some function relation of square root of a square minus x square, it is always beneficial to substitute x as a sine theta or a cos theta, right? So if we simply apply the same relation over here, what we can see, so this particular given relation will simplify to itself as, so if I put x equal to a sine theta, so if I put x equal to a sine theta, then this particular relation will simplify to as, now we already have a over here, so let us let us, okay, it won't matter much, okay, but what is a, basically it is 1, right? So here the a is basically equal to 1, so therefore if you use x is equal to sine theta, now this 1 square root of 1 minus sine x square is basically going to become equal to cos theta plus, and this part, and similarly let us consider y as some sine phi, okay. So this is also going to be equal to plus of cos phi, which is equal to x a times of sine theta minus sine phi, right? Now we are basically tried to simplify the expression in terms of theta and phi. right? Now, why we are doing this, we will try to understand. Now, from here, we can just simplify the trigonometric relation. That is, now this is a very interesting problem actually. So since you are not getting the result from here directly, what I basically thought of is basically to use the trigonometric substitutions. Okay, trigonometric substitutions, right? So from here, if we look at the trigonometric formula, so that is cos of theta plus cos of phi, which is basically equal to 2 times of cos of theta plus phi by 2 into cos of theta minus phi by 2, which is basically equal to a times of 2 times of sine theta minus phi by 2 into cos of theta plus phi by 2, right? So here what we see, that cos of theta phi by 2 and this part get cancelled out because this is not equal to 0. So therefore my simplified solution is basically coming to as cot of theta minus phi by 2 is basically equal to a. So from here I can simply write theta minus phi, because theta minus phi I can simply write it as 2 times of cot inverse of a, right? So I can simply write this as 2 times of cot inverse of a, right? Now why I'm basically trying to do this part, so therefore I got the relation in between theta and phi, which is the argument, right? So if you just now try to proceed back with the given relation, so what we can see, that this theta and phi can be written as sine inverse of x minus sine inverse of y, which is basically equal to 2 times of cot inverse of a, right? Now what if I differentiate this particular relation? So I will get it as 1 upon square root of 1 minus x square plus 1 upon, so minus is there, sorry, so minus square root of 1 minus x square dy upon dx is basically equal to 0. So from here you will basically get the simply relation, that is dy upon dx is basically equal to square root of that particular thing. So from here you can simply write that dy by dx, okay, and there that's how you are going to prove it, right? So there, from there you are basically going to get dy upon dx as square root of 1 minus y square divided by 1 minus x square, right? As simple as that. Is this clear or not? This was a really tricky problem, and I would say definitely it is worth giving a try. Okay, so if you just try to think of the problem in the way that basically I used it over here, because why the intention is coming up, because if you look at the domain of x over here, it is basically -1 to 1, right? Now if you look at the range of sine inverse of theta, that is basically going from -1 to 1. So what if I incorporate that inverse function in it, right? So what if I consider x is basically sine theta and y is equal to sine phi, right? So here a is basically equal to 1, so I'm writing it like that. I am basically mean to say it with respect to this particular substitution, but a is over here is basically 1, so let me write it over here 1, right? So this part of the solution is clear, right? So how did I get the idea that to use a trigonometric substitution instead of using the normal substitution is basically from this particular idea, right? Is this part clear? Is this part clear to all of you? Please let me know if this part is clear or not. Hi Siv, how are you doing? Yeah, which part of the solution is not clear, Siv? Siv Shiny, can you let me know? I will repeat it again. Okay, so let us start. So what I'm basically trying to say is that, so first of all, what I'm doing, I am writing a given relation, right? Now, if you look at the given relation, if you try to find out what is the domain of this particular function, right? So given this square root function, I will first of all try to understand what is the given domain for x and y, right? So for which values of x and y will I have a given output, right? So for real case, your x should be basically between -1 and 1, and similarly for real case of this particular case, your y should also be between -1 and 1, right? So from here what I get the idea. Now if you recall your inverse trigonometric functions, if you recall your inverse trigonometric function, you will understand that the range of sine inverse of theta is basically between -1 to 1, or inverse cos inverse of theta is also between -1 to 1, right? So from that particular idea, what I am doing is that I am trying to consider the substitution, because if you recall from the integral lectures, so if you just go back to the live sessions which I have taken for integrals, you will find out that there is some substitution that I have discussed about, right? So in that substitution, when I talked about the square root of a square minus bx square, in that kind of substitution, or 1 upon square root of x square, a square minus x square is there with a square root term, you're always going to put the substitution x as equal to a sine theta or a cos theta, right? So if I do the same over here, now why I'm doing the same over here? Because if you look at this substitution, I'm basically getting a simplified form in theta and phi, form where I can replace this sine inverse of x and sine inverse of y. Now why did I do that? Because I know the differentiation of sine inverse of x is basically of this particular form 1 upon x, 1 upon square root of x square, and the differentiation of sine inverse of y is basically of the form 1 upon square root of 1 minus y square, right? So when I do the simplification of derivative, I'm basically going to get this particular result, right? So that is what my thought process is, right? So this was a 4-marker problem. So if you have done this problem in this particular manner, you're definitely going to get the full marks. Maybe you can do it in the other way around. So maybe you can proceed the problem from here also. Maybe you can proceed the problem from here also. But in this case, you will have some confusion that how we are going to try to find out the dy by dx term and incorporate for a term, right? Now what you can do, you can just find the dy by dx term and just substitute the value of the constant with the replacing from the given relation. Now that is something you can do to get to the relations, right? So this is clear, right? Is this clear? Is this clear or not? I hope this part is clear, right? So let us now proceed for the next set of MCQ types of problems that are also been asked in the CBSE previous year problems. So if you just look at the previous year problems of the type, I basically come up with all the types of, so I'm basically generally showing you all the different types of problems that is formed basically on the type of relations. Okay. So the first problem, if you look out over here, it is said that you have a given set A, which is basically containing the elements 3 and 5, right? Now, you have to basically comment on a number of reflexive relations on A is. So, if you look at this set A, 3 and 5, so if I need to make it a reflexive relation, I need to have 3, 3 and 5, 5 belonging to this particular relation, right? So, therefore, our relation must have 3, 3 must have 5 comma 5 must have 3 comma 5, right? So the number of reflexive relations on A is basically equal to, so how many reflexive relation is possible? So if I have, so how many, therefore a relation can be like this 3 comma 3 and 3 comma 5 on A, right? Similarly, I can also have 5 comma 5 and 3 comma 5 contained in the relation. So these two relations are all reflexive relations, right? So from here, and similarly, this particular relation is also going to be a reflexive relation, right? Is it clear or not? Please correct me if I'm wrong. But if you look at by the definition, what is most important to understand is that if 3 comma 5 or x comma y basically lies in the relation, then x comma x should belong to the relation, right? But here in this case, I have 3 and 5 as the elements of A, right? Basically belongs to the element of A. So therefore, I should have 3 also in the relation and 5 is also in the relation, right? So I should have 3 comma 3 as the order pair given in the relation, and I should also have 5 comma 5 in the order relations, right? So therefore, combining all this, you can see that the minimum number of the reflexive relation that is possible is basically 2, right? But now one more thing is to understand is that what is the total number of relations possible, right? So that is an important problem. So relations are basically subsets, right? So total number of relations. Now, if you just recall, total relations, total relations from from A to B such that the cardinality of A is given as some m and the cardinality of B is given as some n. So total number of relation is basically given as 2 to the power m into n, right? So if you just look at, so since here the definition of A and B is not given, but only A is given, right? So we can see cardinality of A is 2, but the cardinality of B is not given. So in this case, I cannot comment the total number of relations possible, right? But in the problem where it is basically asked for the total number of reflexive relations, so I can comment that the number of reflexive relations is basically equal to 2. Okay, so this is something very simple. Similarly, if we have the next problem, we see that there is a relation on the natural number, right? We have a relation on the set natural number given as A is equal to B minus 2 such that B is greater than 6, right? So if B is greater than 6, then let us put B is 7, right? So if B is 7, then I have A is equal to 5, right? So therefore from here, if B is 7, A is equal to 5, right? Similarly, if I put B is equal to 8, if I put b is equal to 8, I will have a is equal to 6. So therefore, what I can see that option number B basically satisfies the given relation. So therefore, our answer to this particular problem is going to be option number B. These problems are very simple, so I request the rest two problems basically you can try it out as a homework. Okay, so if you try these problems as homework, you will understand that all your concepts are going to be very crystal clear. Okay, so please try to solve these problems and try to get to the answer and let me know in the comment section while you are completing the solutions. Okay, so let's try to understand what the next set of problems that is possible is that. Now also one type of problem is that given with a given function, with a given definition of function, you are basically to predict on the type of function, whether it is a one-one function or not, right? So I am solving the first part or the first question, that is I have a function which is within the domain where it is involving all the real number except minus of 4 by 3, and it is going to the all real numbers, right? The function is defined as y is equal to 4x divided by 3x plus 4. So if you just look at this, you will find that the domain will include x belong to all real number except the point where the denominator is equal to 0, that is minus of 4 by 3, right, which is already given in the problem, right? Now our turn is basically to understand how do we basically find out the range. So for range, what I will do, I will consider this part is equal to 4x y is equal to 4x divided by 3x plus 4, right? Now I will try to replace x in terms of y. So what I will do, I will try to multiply this part, right, and I can write like this. Similarly, so I can just simplify the x in terms of y. So what I will do over here, I will take 4x minus 3xy is basically equal to 4y. So from here I'll get x as common, so I can write this as 4 minus 3y is basically equal to 4y. So from here I will get x is equal to 4y upon 4 minus 3y, right? So if you just try to express x in terms of y, so from here you can see that x is possible for all values of y given real number except the point where it is basically equal to minus 4 by 3 plus of 4 by 3, right? So therefore you can see that the range of this particular function is also all real number except the point where it is 4 upon 3, right? So you can see it is not equal to all the real part, right? So except one point, it is always equal to the real part. So therefore it is not an onto function, but it is not an onto function, right? Now I have to discuss about whether it is a one function or not. So I have told you, so in order to check for one function, what you can do, you can try to find the derivative. Okay, so if you just try to find a derivative, you will see that this kind of function is basically a one function. Okay, so that is how you're going to classify and come up with the result in the examination. So if you understand this part of the problem, please let me know in the comment section with the answer that you're getting for 30T. Okay, so please try to solve this problem as a homework problem and please let me know with the answers of it. Okay, so I will share these PPTs with you in the Telegram group. Please don't forget to join the Telegram group from the description box. Okay, so with this, with this I am ending the session. Okay, so we have almost covered all the parts of the questions and we have discussed about the some recap on the type of relations and type of functions. So what we understand is that the most important sets of problem is basically on the classification of functions and classification of relations, and there are some proof that types of problems on relations and functions, right? Now if you are looking in purpose of the one marker problem, then those kind of problem like number of functions, number of relations, those are also equally important. Okay, so that is something that you also need to focus equally. Okay, so with this I hope you have understood everything clearly. Please let me know if something is not clear. Okay, so with this we are approaching the end, and so I hope you have understood everything in this particular session. So if you haven't understood anything, you can definitely let me know in the comment section. Okay, I will be looking for your comments, and I will definitely look for your outcomes of it. Okay, so we know that we are already proceeding with the CBSE examination, so definitely your preparations are going nicely. So with this we complete the entire syllabus of class 12 board exam for maths purpose, and now we are going to proceed with the some mock test, and we are definitely going to see some top 10 important questions which are important for your CBSE purpose, right? So stay tuned for that. So if you haven't liked and like this particular video, please make sure that you like the video and don't forget to subscribe to the particular channel. So with this, I come to the end and I wish all of you good luck. Thank you.